Hi everyone, my name is Bruce Moravchik. I'm the coordinator of the NOAA Planet Stewards Education Project, along with my colleague Molly Harrison, and we are very proud this evening to bring you Hurricanes and Robotics, how new technology is changing the way we study and predict extreme storms. For those of you who are just joining us, I recommend that you take a screenshot of this screen in the event if you lose the connection or possibly have an issue hearing through the VoIP. You may always dial in. So without further ado, I'd like to just go through a few announcements before we begin our presentation by Dr. Travis Miles. So first of all, tonight's broadcast is being recorded, and I will be sending you a link to the video archive within a week. If you don't receive a link or an email within a week, please do send me an email with the subject, request a link to the May 13th webinar. Now, a video archive and all of the slides that are being presented tonight and of all broadcasts from NOAA Planet Stewards going back to 2013 are available on the NOAA Planet Stewards Google website. The link is there. The link will also be in an email that I send you after the webinar. So if you want to get back and you want to see all the slides, they are currently available. Now, if you can't access this archive website, you can either send an automatic access request through Google, or you can send me an email with the subject request access to the Planet Stewards Google site. You will need to have an active Google account in order to access it. For this evening's presentation, all attendee microphones will be muted. If you do want to ask a question, please type it into your GoToWebinar control panel. We will do our best to answer as many questions as we can during the time frame of the broadcast. And also during the broadcast, I'll be sending you out an email with a link to a post-webinar poll. Please, as soon as you're done with the webinar, just open your email, take this. This will take you literally a minute, and it does give us important information and help us prepare for future events. Everyone who attends the full period of the webinar will be receiving a certificate of attendance denoting an hour of contact for professional development. Now, again, before we begin, I would like to thank everyone who came to and represented NOAA Planet Stewards at the National Science Teachers Association National Conference in St. Louis, Missouri last month. Amelia Cook, Angela Guspradek, Ben Graves, Rick Jones, many others who represented and presented on behalf of Planet Stewards. I also want to thank Peg Steffen, our coordinator emeritus from Planet Stewards, who was there and representing, and certainly Teresa Damiani, who gave the AGU presentation representing NOAA. It was wonderful, and everyone who came out and were part of NOAA Planet Stewards. I'd very much like to thank Carla McAuliffe from the National Earth Science Teachers Association for the wonderful job that she and the organization did to honor all NOAA Planet Stewards at their reception and continually throughout the conference. And also would like to thank Wendy Abshir, the education director from American Meteorological Society, for all the work that she and her team did on behalf of NOAA Planet Stewards and what they do every day for Earth Sciences. And speaking of Earth Sciences, the Earth Scientist, for those of you who are not familiar, is the peer-reviewed journal of the National Earth Science Teachers Association. NOAA Planet Stewards are featured prominently in the spring 2019 edition, which is the new edition right over here. It's available for free and online at this link. We'll be sending this out later on again. And also in the spring 2016 edition, NOAA Planet Stewards and their stewardship projects are represented, as well as many programs from NOAA's National Ocean Service that you'd certainly want to find out more about the NOAA Marine Debris Program, the National Sanctuaries Ocean Guardian Program, and many, many others, including citizen science, gaming, everything like this. So have a look. It's really terrific. And for those of you who are interested in more face-to-face and hands-on, NOAA Planet Stewards is joining up with the National Estuarine Research Reserve System, and we're holding a 3-day workshop in Charleston, North Carolina, Becoming Estuary Stewards. Those of you who want to get out and explore salt marsh dynamics, work with data with real marine researchers, learn about projects that your students can be doing with real-world examples, bring home standards-based STEM lessons. This is a wonderful, wonderful workshop, and the folks over at the ACE Basin National Estuarine Research Reserve, as well as folks from South Carolina Sea Grant. I'm sorry, I should have said South Carolina. I apologize. South Carolina Sea Grant will be there. It's going to be a wonderful event. I will be there as well, taking part. And finally, for those of you who may be joining us who are not getting The Watch, The Watch is a bi-monthly newsletter from NOAA Planet Stewards that contains almost all free professional development opportunities, resources, and educational materials. If you do not currently get The Watch, then I really recommend that you sign up for our email list. You can always unsubscribe, but it is certainly worth it. A lot of very worthwhile, very timely resources are here. So with that final announcement, I would like to turn the table and the mic over to Dr. Travis Miles for this evening's presentation. And as we begin, Dr. Miles, your mic is muted. I just would like to introduce him to everyone. Travis Miles is an assistant professor in the Department of Marine and Coastal Studies at Rutgers University in New Brunswick, New Jersey, where he also received his doctorate. He was a Fulbright Scholar at the University of Gothenburg in Sweden and was the recipient of the 2019 Marine Technology Society Young Professional Award. As core faculty within Rutgers University Center for Ocean Observing Leadership, he specializes in using networked ocean observing systems, including autonomous underwater robots, remote sensing technologies, and predictive ocean and atmospheric models to study air-sea interactions in storms. A large focus of his research includes improving hurricane intensity forecasts in the hours before they make landfall. And with that, I'd like to welcome Dr. Miles to take the mic. It's all you.
All right. Thank you for that wonderful introduction, and thank you for having me. And thank you to everyone for joining me this evening. Today I'm going to be talking about hurricanes and robots, how new technology is changing the way we study and predict extreme storms. So I am at Rutgers University. I've been studying this for a few years. It's one of many, many things that we do at Rutgers, and it's just something I'm very excited and passionate about to share with you all. Before I get started on the exciting hurricane stuff, I'm first going to tell you where I sit in relation to NOAA. All right, so the first thing I'm hitting you with is this graph, this organizational chart. So this is big NOAA up here. So this is Department of Commerce, NOAA, National Weather Service. This is where your daily forecasts come from. The national centers, this is where your National Hurricane Center is. Over here is Ocean Service. This is how I'm connected to this. So the first way I'm connected is through the Integrated Ocean Observing System. There's 11 regions within the Integrated Ocean Observing System. One of them that I'm in the Mid-Atlantic, is MARACOOS. This is the Mid-Atlantic Regional Association Coastal Ocean Observing System. There's one for every region of the US, and they're made up of many, many different academic institutions. So I'm at Rutgers. I'm one of many regional members of MARACOOS, but each of these has lots of different universities. And what we do is we develop ocean observing systems that support all of this. So there's a lot of ocean observing systems within NOAA, but this is the way that academic institutions can play a role in ocean observing. IUS is part of the global ocean observing system. So not only IUS is our kind of regional US piece, but we're also connected to global observing systems across the world. So there's this huge system that's doing a lot of this type of stuff I'm going to share with you today. And our academic institution, oh, I want to get that one. Our academic institutions are actually regionally, we're certified by the federal government. So we're at our lab. I'm at my lab at Rutgers. I do all my quality control. I collect data, and it's just as federally certified as the data that NOAA collects on its own. So I just want to get that out there because I'm not sure people generally know that academic institutions are actually providing real data that helps with your forecast, both ocean forecast and atmospheric forecast every day. So as I get into hurricanes, I'm already going to start off with our poll question number 1. So I think Bruce is gonna kick that off.
Okay, so we're just going to take about a minute. Please just move your cursor right over your answer. Have you ever experienced a hurricane firsthand? Okay, we'll give everybody just another few seconds to answer, but that looks pretty good. All right, Travis, can you see the answer there?
Yep.
Terrific.
So yeah, I'm not surprised to see more than half. So it's 61% of the people on the call, and 39% have not. I personally have been in about 12 to 14 hurricanes, depends on, head away. 12 to 14 hurricanes, and then last year by accident, 1 typhoon. If you guys look at this map, I'm sure you can pick out, I think I lost my mouse. Okay, anyway, there it is. I'm all crazy. I'm sure you can look at this map and pick out the storm that you've been in. Hurricanes or tropical cyclones, as they're more uniformly known across the world, they happen most frequently in the northern hemisphere. They impact Asia in a very significant way, and a little bit less here in the U.S. So we get significantly impacted. Asia gets about 3 to 4 times as many storms as we get on a given year. I'm going to be focusing mostly on the East Coast of the U.S. For this talk, but a lot of what we learn here in this area, we're also doing similar work off of Korea and China, and then in the Bay of Bengal as well. So the Mid-Atlantic of the US and the East Coast of the US, these are my test laboratories. All right. So why do we care about hurricanes? So it's not just that they occur in these places. These places also are some of the world's mega regions. So this is where you have some of the largest populations at the coast, like up here in New York City, and then down along the East Coast of the US, a little bit into Florida. And then also these mega regions off of Asia. So this is Japan and Korea. Keeps jumping around. All right. Japan and Korea, and all through China. So these places are all in Hurricane Alley. right where most of the storms make landfall. So a little bit of statistics. So this is a table of billion-dollar events that have affected the US since 2018. Tropical cyclones have caused over 870 billion. I think this is a little behind. I think with 2018, it's over $900 billion in damages. That's more than all other natural disasters combined. So it's a massive amount of damage and a massive amount of economic loss. But more importantly, they've killed a lot of people. They've killed over 6,000 people since 1980, and that's again similar to all other natural disasters combined. So between damages and loss of life in the US, they're a really, really challenging thing to deal with. And this is just in the US. So internationally, these problems are much bigger. Not so much in dollars, but in human lives. So this was one storm, Cyclone Nargis in 2008. I want to take you to take a minute and think about where you were in 2008. That wasn't that long ago. 138,000 people were killed by one cyclone with 48-hour warning. So even with 2 days warning of a good storm track and intensity, there's still this loss of life in the developing world. So it's a really serious thing, and it's something that if we can make small improvements, that can have a really, really big impact. All right. So what's our first line of defense against these storms? With Cyclone Nargis, a 48-hour warning wasn't enough. But what we want to do is keep increasing that warning time and enabling people to make educated decisions when they need to evacuate, when they need to shelter in place, and what they need to do. So the first line of defense, an accurate track and intensity forecast. So how are forecasts made? I put this really terrible plot up here with a lot of acronyms, but I'm going to go through each part of it with you. But this is generally how a hurricane forecast is made. So to start, we collect data. So the first thing that happens when there's potential inkling of a storm is we look at all the different data sets. So National Hurricane Center will do this. They'll look at all the different data sets that exist. Usually that's satellite data, ships and buoys, aerial reconnaissance, radio sounds, which are essentially dropped probes out of planes, look at radar, and then I don't even remember what ASOS is off the top of my head. So we collect all this data. We take that data, we ship it off to the National Hurricane Center directly, but it also gets ingested into weather models, these atmospheric and ocean models. And those weather models, there's some that are numerical models that are similar to what gives you your daily forecast of rain or winds or whatever it is. And there's statistical models. We don't have to get into the details, but basically that data feeds into the models and the models start running. So puts out model output comes out, and that model output is looked at alongside the observational data directly by the National Hurricane Center, and a forecast is issued to local communities. So one thing I want to make clear is that people make forecasts. The models just give some sort of output or some sort of guidance. It's people that are actually looking at that data and making an actual forecast and issuing that guidance. So when we talk about improving our hurricane intensity forecasts, it's not just making our models better, it's also making our people better. So understanding processes, learning about the ocean, learning about the atmosphere can really help improve forecasts just with our knowledge. So this is one forecast cycle, and basically every 3 hours, every 6 hours, however long it needs, however much time between them, this cycle is redone over and over and over until a storm makes landfall. So the key part I'm interested in as a ocean and atmospherics and scientist is mostly this data part. So we'll come back to that. But I want to make sure that we have the right data that we need to make these, to have our models run correctly, but also to make those good forecasts. So right now, how are we doing at forecasting? So slow down a little bit on this one. So this is from National Hurricane Center. This is the average track errors for the Atlantic Basin. So I'll explain what this means. On the y-axis here, this is forecast error in nautical miles, and then year is on the bottom. I'm going to focus in on this yellow line, which is a 72-hour forecast line. So this is what's going to happen 3 days from now. That's about 3 to 5 days is about what you need to make an evacuation or shelter-in-place decision. So I focus on that line. So since 1970, in 1970, we were doing, we had about a 450 nautical mile error on average. So, and that's in 2015, that was reduced to about 100 nautical mile error. So what that means is in 1970, if you had a storm coming at the Mid-Atlantic region, 3 days out, we could say, well, it might hit North Carolina or it might hit Cape Cod. So today, we can do much better than that. We can say, well, it might hit near Philadelphia or it might hit New York or a little bit of Long Island. So this has been a really incredible improvement over that time period. This is not what state it's going to hit, but what city is a storm going to hit. Why has that improvement happened? First off is the advent of satellites. So we have an immense amount of data about exactly where a storm is, looking at the cloud tops, looking at how it's evolving in time and space. We've had the hurricane hunters going since the 1940s, collecting immense amount of data, collecting more and more advanced data. And so they've really reduced those track and intensity errors. And then most importantly at this point is supercomputers. So we've been able to run numerical models over and over and over and over again to come up with our best guesses at where a storm might make landfall. All right, so that is track. This is average intensity error. And when I talk about intensity, I'm actually talking about the maximum wind speed. That's the standard way of talking about storms. It's not the only way that you can have damage. You can have damage from flooding, from rain, things like that. But wind is typically how we gauge the strength of a storm. So here we have forecast error in knots. So this is nautical miles per hour. It's close to miles per hour. And again, if you look at these, this yellow line, which is 72 hours out, and this is year on the bottom, forecast error on the y-axis, you can see we've gone from about 20 knot error to about 15 knot error. So that means when they make a forecast and they say it's going to be X strong, there's could be 20 knots either stronger or weaker than that on average. This depends on the storm and the conditions at any given point in time. So we've made a factor of 3 improvement in track error, but we've only made about a 20 to 30% improvement in the intensity error. So we still have a lot of work to do. We might know where they're going, but we don't always have a good idea of how strong they will be. Okay, so why is this? So there's limitations on hurricane intensity improvement. Well, I know I said supercomputers have been part of the answer for track, but we still need more for intensity. Intensity is very complicated to get. You need very advanced models with lots of high resolution that are run very quickly. And we still don't quite have enough power to do that, enough computing power to do that. But I want to open up my second question. What else is holding us back?
All right, so what can affect a hurricane's intensity? Please place your best answer on the screen. Ocean temperatures, wind shear, dry Saharan dust, all the above or none of the above? We've got just a few people who haven't voted, so come on, give us your best guess. All right. Here we are.
Awesome, you're all right. My favorite one, ocean temperatures, and I guess all of the above. It is all of the above, but ocean temperatures is a great second guess because that's the one that I study the most. All right, so I guess we can jump back over. Okay, so how does a hurricane work? I'm going to go through some of those different limitations on our understanding of hurricane intensity. So this is a cross section of a hurricane. Here you can see the eye wall right here. You can see these rain bands that are moving outward in these orange arrows. They're pointing up. And basically what happens is you have, as a storm's already formed, you have this warm ocean sitting above a cooler atmosphere. And that warm ocean, there's moisture and heat that come out of that ocean and into the atmosphere. Now, as air heats, it rises. And as that air rises in the center of the storm, or in these rain bands in this eye wall, as it rises, it comes up, it cools down, and it either moves out, and that's why you get this sort of flat top, flat top of the storm. But it also cools and moves back down. It falls down in that center. So you get this very clear area with falling, cool, drier air. It comes down to the bottom and it's cold, the ocean's warm, it warms back up again. So what can happen from wind shear? So when you have no vertical wind shear, your storm looks like this. It's a perfect kind of tube. Air, it can go through this process pretty easily over and over. Wind shear is basically when you have strong winds at aloft and weaker winds as you keep going down. And basically it'll tilt over your storm and you don't get the same, that same circulation. You don't get the perfect kind of upflow outward and down. It interrupts that, that circulation pattern. And it can kind of break the storm's organization apart, and it doesn't quite work as well. So when you hear in the news, vertical wind shear is really ripping a storm apart, it's actually talking about this. It's talking about this tilting over from those winds. So that's one thing that can limit the intensity of a storm. The other thing is that dry Saharan air. So this is actually dust off of, this is dry air. You can have high dust in it. So, and when that comes into the hurricane, it really tamps down the moisture and you don't get as much energy out of the ocean and up into the upper atmosphere. So those two pieces can act to weaken storms, while the ocean acts to power it up. So wind shear can rip it apart. Dry air can reduce the amount of heat coming up into the upper atmosphere, but the ocean is that fuel source. So here's two maps, and I'm going to start on the left. This is tropical cyclone. This is Hurricane Katrina in 2005, and this map is of heat potential. So this is the amount of heat actually in the ocean, not just at the surface, but the thickness part, the thicker. The thick ocean. And what you can see, this is the track here of Hurricane Katrina. It's weak through this area, goes across Florida, goes across this low heat area, and then as it moves over this really warm water, it powers up all the way up into a Category 5. It weakens just a little bit right as it leaves that warm water. It makes landfall around New Orleans. Over Hurricane Maria, you can see the same thing. So this is heat content, which is essentially the same as heat potential, this tropical cyclone heat potential. Here is the ocean heat content is the map, and then the category is on the line. So you can see weaker storm, Category 1, goes over those warmer waters, powers up rapidly to a Category 5, makes landfall in Puerto Rico, and then it weakens again, but stays strong until it really peters out as it goes up into the Atlantic. So, okay, I think I have another poll question coming up. Oh, maybe not. So I mentioned this in the past slide, that this is a thick layer. Oh, there's poll question 3. I might have given it away. Poll question 3 is down there in the corner. So,
Okay, so poll question 3. What ocean temperatures matter for hurricanes? Surface temperature, bottom temperature, upper ocean temperature, or, hey, temperature still doesn't matter. Travis, do you feel that any of these question or answers need any clarification, or you feel comfortable?
they probably need a little clarification, but I'd like to see what people get.
Okay.
Make them think about it.
There you go. All right, why don't we just take a few more seconds while people think about this.
So the clarification I'll give a little bit. Surface temperatures, I really mean the very, 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 very surface. So the skin temperature, as it's called in meteorology. Bottom temperatures all the way at the bottom of the ocean. Upper ocean temperatures, so that's kind of the upper thick layer. And then, of course, the last answer, which only people who are angry at me are going to click on.
Okay. Let's see what people said.
All right. Great. So surface temperatures and upper ocean temperatures. All right. So the correct answer is the upper ocean temperatures. So this about the surface down to 200 meters depth. So it's not just those temperatures right at the surface, because what happens is these high winds and high waves from hurricanes will actually mix through the surface layer of the ocean very rapidly. They can actually mix down to 200 meters or deeper in some cases in the ocean and pull up cold water. And if they do that, they can actually pull up that cold water and de-intensify themselves. So when we want to do hurricane prediction and we need to know how much fuel there is, how much energy, we can't just look at that surface from satellites. So satellite sea surface temperature, here's an image. You can see that top image is some features. So that's the Gulf Stream. You can kind of see the shape of Chesapeake Bay and a warm core eddy. But then if you look at observed upper ocean temperature, you see there's this cold water beneath it. So if we have our satellite and we see this warm water, we may say, wow, it's just going to really strengthen up. But there's actually this could be cold water hidden beneath it that might weaken it. So we need to have data underneath the surface of the ocean. The only way we can see, the main way we use to look at ocean temperatures is from satellites in hurricanes or ahead of hurricanes. Once those clouds come over, we can't see that. But we really don't have a good way at looking at the upper ocean temperature, so that profiles of the ocean. So that gets to how do we sample the ocean? What data is out there now to really look at that deeper ocean heat? So this is a map of all of the observations from the 2018 hurricane season from what's known as the Argo program. So these are floats that are out there all the time collecting temperature, sometimes salinity, but almost always temperature, density, and pressure data. So if they have salinity, they're getting density as well. And so this is a whole summer's worth of data from that program. Now this looks pretty awesome, right? There's a lot of data here. Each dot represents a profile. Argo drifters or Argo floats take a profile every 10 days. So not a really rapid update time, but there's lots of them out there and lots of people put them out there. But one thing you might notice when you look at that is that there are gaps. Specifically, see if my mouse comes back. Specifically, you see gaps in those blue areas at our coastlines. Not quite. Right. So you can see off the coastline of the Mid-Atlantic, off of the South Atlantic. I don't have a mouse. And you can see a lot of blue, which is basically the bottom the bottom of the contour of the ocean on this map. So all those places where we don't have Argo profiles, that's where hurricanes make landfall. Like Florida, many of them can hit the Mid-Atlantic Bight, Gulf of Mexico. So there's a huge data gap of places that we need to collect more information in order to understand what the ocean heat looks like and how we get that into the atmospheric models. So how do we collect more data in the ocean during these conditions? So this is going to be my first break point. If people want to ask questions, I'm going to kind of move on to answering this question. So if anyone wants to ask any questions, this is a great time. We can take a few minutes to do that. And hopefully my mouse will come back while we wait.
Good luck with your mouse, Travis. In the meantime, if anyone has any questions, please type them into the question box on the control panel from your GoToWebinar. It's on the right-hand side of your screen. You can expand your control panel by clicking on the orange arrow, which is on the upper right-hand side of your screen. We actually do have some questions coming in now. Travis, the first question is, are there Argo floats out in the Pacific, say around Hawaii?
There absolutely are Argo floats in the Pacific. There's tons in the Pacific. I think I just showed the Atlantic, but there's basically anywhere that there's deep water, you usually have an Argo float. The main limiting factor to getting Argo floats out there is that they are deep profiling. So they'll sit at the surface, get programmed, then they'll dive down to 1,000 meters depth, and they park there for 10 days. They'll sit there for 10 days, and then they'll come back up, do another profile, send that data back to shore in real time. It'll get assimilated in these ocean models over and over and over again. Argo floats can stay out for about 4 years doing that. So they're out there for very long periods of time. One challenge with them, though, is that they have to go those deep depths, so they won't stay on the shallow continental shelves. And they're floats, so they drift with the currents. They go wherever the currents take them, and they don't have any control. So you can go to that website back on the slide here, and you can go see what Argo floats are out there today. There's many out there. You can click on any of them on that website, and you can look at data in real time, and they're a great tool to use. We use them all the time for teaching, but also just for data, for research. And so you can thank this program actually for a lot of our weather forecasts. They've really revolutionized our standard weather forecasts on a daily basis.
And Travis, I'm guessing that because these Argo floats are such deep profiling floats, that this is why you have a gap along the coasts, correct?
Yeah, absolutely. Since Argo floats are designed to go down to 1,000 meters, they don't do very well on shallow continental shelves where most of us live. So usually they'll if they get drift inshore, they'll kind of go down and they'll hit the bottom, drag along the bottom or something like that. But the physics of the ocean kind of keep them offshore all the time. If we deployed them right off the coastline, they'd eventually get advected offshore, and they kind of wouldn't come back very easily.
So, I mean, how often are Argo floats lost?
So at some point and some day, every Argo float is lost. They're designed to be cheap and relatively disposable. I know we talk about the ocean garbage patch. This is a very small program relative to the amount of pollution out there, and they're collecting really vital data. They can stay out on their batteries for about four-ish years, but eventually they run out of power and they'll sink to the bottom and rest there. So there might be someone at the Argo program who could answer questions about marine garbage and Argo, but they're a very small percentage of what's out there if anyone's concerned about that. But they're a hugely vital resource for how we do weather oceanography, how we do climate research. They really are key to keeping our climate models on track and giving us good results as we move forward.
Okay, why don't we, there are more questions, but why don't we, continue with the presentation. We'll be sure to address questions after, the next break or at the end of the presentation.
Great. Okay, I got my mouse back. So I cheated a little bit. This isn't in a hurricane. This is out in the Antarctic doing some work. But this is still probably pleasant compared to what being on a boat out in a hurricane would be like. Boats are our key way of getting ocean data, and they have been for many, many, many years. But there are other options. So you guys came to hear about robots and hurricanes. So I've talked about hurricanes, and now I'm going to talk about robots. This is one of my favorite topics. So the Slocum mission. So Joshua Slocum was one of the first people to, the first person to solo sail around the world. In 1989, Henry Stommel wrote this science fiction article. And the science fiction article was about ocean robots patrolling the oceans, collecting data, sending that data back to shore, being controlled from a lab like this that you see on Nonomet Island. So this is the science fiction version of the Slocum Mission Control Center. There's this great quote by Henry Stommel, and it's that the payoff and increase of knowledge often is greatest the more unconventional the idea, especially when it conflicts with collective wisdom. A lot of people thought this idea was crazy, that the idea that you could put anything off the side of a boat and talk to it for weeks to months on end, control where it goes, send data back to shore, and really change the way that we do science. People thought this was crazy. But a guy named Doug Webb, an engineer who knew Henry Stommel and lived nearby, didn't think it was crazy. And this was his first schematic of what an ocean glider or a Slocum glider would look like. So in this setup, it would be this torpedo-shaped system with an antenna that sticks out of the surface of the ocean, and it goes about its merry way. I'm not going to talk too much about how they fly yet, because I have one more poll question. So in 1989, the idea of this patrolling glider that could stay out, this patrolling robot that could stay out for months and even years on end was science fiction. 10 years later, they built one. So from 1989 being science fiction to 1999, they built the first Slocum glider. So this is Doug Webb, the creator of the Slocum glider, and that's Clayton Jones on the left, who is the current head of Teledyne Web Research. And they're standing on a dock at Rutgers University Tuckerton Marine Field Station. So the one thing that Henry Stommel got wrong was that this would be a revolution out at Nonomet Island. It was a revolution that actually started in New Jersey. So New Jersey has a long history of oceanography. Web Research is located in Martha's Vineyard or in Falmouth, Massachusetts, so we share it. So this is Doug Webb 10 years later. And what they did is they created this Slocum glider. They tied a rope around the tail. They put it off the dock. They had it go down in the water and come back up. And it came back up. Everyone cheered and they declared success. So that's 1999. Well, 2009 at Rutgers, with our students piloting and with our students working with the data, we crossed the Atlantic Ocean. So we went from New Jersey all the way to Bayona, Spain, with a Slocum ocean glider. And so if you go to Bayona, Spain, and you go to where the Pinta is, where there's plaques at the museums, there's actually a plaque that shows RU-29, Rutgers University 29 Slocum glider, next to that plaque of the Pinta. So this is a really, really rapid revolution, going from 89 science fiction, 99 building the first prototype, 2009 crossing an entire ocean basin. So where are we today? So this is just the Rutgers and our partner statistics. So we've done over 477 deployments. That's 236,000 kilometers of ocean that we've covered, and that's 12,000 days at sea. So in just 10 to 20 years, we've actually collected 12,000 days of data. And we've deployed these across the world, from big ships to these small rubber boats. This is in Sri Lanka. This is actually one being pulled back on the boat after Hurricane Sandy. This is one in Antarctica, and I don't remember this one. It's probably in the Mid-Atlantic Bight. But you can see we've covered many ocean basins, circumnavigated the South Atlantic, worked along the West Arctic Peninsula, so all over the world. And so beyond just Rutgers, there's a lot more lines on here now from different partners that have worked on this across the world. And we're actually hosting an international meeting at Rutgers next week with all of those partners, with over 200 attendees from different organizations across the world. So, poll question number 4, before I move on.
So how do ocean gliders swim? Propellers, jets, gravity and buoyancy, or magic? It's magic, isn't it?
It's always magic.
All right, so we'll keep the poll up for just another few moments. Everyone take your best guess. All right.
Okay. So it actually is gravity and buoyancy. So good job. We do have propellers on some of them now, but they're not to really make it do most of its swimming. They're there to just do a little extra work when we might need it. So I'll go through how they operate on the next slide. Thank you. Okay. So this is a glider taken apart, ripped apart into a few different pieces. And so basically they're these very, very simple, actually, systems. They have these aluminum hulls. Some of them now are carbon fiber. They have a buoyancy pump. So this is, I'll go through in a second. This is what pumps in water to make it heavy and pushes it back out to make it light. Here's all the brains of the glider in the back. So this is what's telling it how to operate. Here's an air bladder in the back that puts its tail up when it's at the surface. And here's its communications. So we have Iridium, which is a satellite cell phone, and then FreeWave for short distance radio, and then GPS, and then also this Argos, which is the same communication system that the Argos floats use. And then there's an altimeter, and I'll go through how all those things work. The most, aside from the glider itself, the most important thing on here is the science payload bay. So here, this is a CTD, which is a conductivity, temperature, and depth sensor. But basically, any sensor you can fit in that payload bay, we can deploy. So it's gone from simple sensors like CTDs all the way to giant optical sensors that stick out of the system and look at particle sizes. We can look at ocean acidification. My collaborator, Grace Saba, is setting up an ocean acidification network in the Mid-Atlantic with gliders in it. There's all sorts of things that you can put in here. And as we develop new technologies and new sensors in different fields and they become more miniaturized, we can package those things into these gliders. One thing you don't see in this picture are the batteries, but generally these operate on alkaline or lithium batteries. They're new rechargeable batteries. The alkaline batteries, they're actually packs of Duracells that are packed around this area and then this area in the back. A standard alkaline deployment can be for about 30 days, whereas lithium standard can be about 90 days. But we've managed to go, like I showed, across ocean basins up to a year with lithium batteries if we do a lot of work to control how the glider flies. Now, how does the glider fly? This was my question earlier. So at the surface, it pumps in that water into the nose area, and it actually reduces the volume. When you reduce the volume, the glider descends. So you can think about, if you've ever been scuba diving, if you push the air out of your buoyancy controller, you've reduced your volume, and you fall toward the bottom of the ocean. Now, if you put air back into that bladder, you've increased your volume, and you rise through the water. So gliders operate in this yo pattern. They'll go down, so they'll suck in all that water. They have a set pitch angle, and they'll fall using gravity, fall through the water column. With the wings and the shape of the body and the set pitch angle, they fall forward. So they don't fall straight down like the Argo floats. These actually fall forward very slowly. They reach the bottom or some programmed depth. They can sense the bottom with an altimeter, and then they'll use a pump to increase the volume, so essentially push that water back out and rise back up through the water. So it will do that over and over and over again, hundreds and hundreds of times throughout one deployment. So they fly this sawtooth pattern, or YOs as we call them, and they collect environmental data along their path. The environmental data, so the sensors, they usually collect data about every 2 seconds. These fall pretty slowly through the water column at about 10 centimeters per second. So we get very high resolution data. We get a lot of information. And so they fall at about 10 centimeters per second. They move horizontally. It's about 20 kilometers a day. So they're relatively slow. They have to go a little bit faster than ocean currents. If they get caught in a really strong current, we kind of have to navigate them out. But we can't talk to them while they're underwater. So in order to navigate them, they have to come to the surface. They have to acquire a GPS, just like your phone does. Oh, come on. They communicate back to shore, so they'll send any data that they collect all the way back to shore, and they'll download new instructions, and they'll move on their way. So they're semi-autonomous. Usually someone has to keep up with them maybe once every day. We'll look at what they're doing depending on the situation. If it's a hurricane, maybe we'll look at it every couple of hours. When we were crossing the South or the Atlantic Ocean, we maybe looked at it once every 3 or 4 days because it was basically just going down and up very slowly for a very long period of time. Here's a 3D rendering of kind of what the data looks like. So this is probably salinity, but you can see the blue where it's fresh, and then the red where it's salty, and you can see this line of YOs. So this is actually probably a scatter plot of data. So you can see a ton of data is collected, and you can see these very clear ocean features. Now, when that data gets sent to shore, it actually goes to shore in near real time. So within a few, maybe 30 minutes of it calling home, that data is sent to shore. It's sent to the Integrated Ocean Observing System Data Assembly Center, which is a federal data repository. It's packaged up, and it's sent off to be used in ocean models for the Navy, for NOAA in real time. And it's also then, those models are then coupled to atmospheric models. So you can see where this is going for hurricanes. So in addition to doing this type of work, like I mentioned, we collect all sorts of data for water quality, oxygen, things like that, all over the place. Now, at the same time gliders were being revolutionized, there was something else happening. So again, this is that same place at Rutgers. It was an incubator for ocean observing since 1989. So this isn't just about gliders. You can kind of see it down here in this hand-drawn picture. And this is an ocean observing network. This is called the Long-Term Observatory. You can see these cables all over the place. You can see some robots in the picture. And And so this is Fred Grassley, who started the Rutgers Institute of Marine and Coastal Sciences. And he dreamed up this idea of having this long-term observatory, this omnipresence in the ocean, or telepresence in the ocean. Because what's better than one glider working by itself? It's a fleet of gliders working with all sorts of other ocean observing systems at one common goal. So from this vision, it came into reality within 10 years, some version of this, not quite this dense, but this was the dream in 2001, to have moorings, to have robots working, boats at the surface, and coastal stations doing their job, all at one goal. So 10 years after that, or not 10 years after that, but over the next 10 years, IUS started being developed, the Integrated Ocean Observing System. Now this is the NOAA IUS that I mentioned earlier, and they really implemented this from this really high density ocean observing system to a broader regional observing system with similar pieces all in it, and then also the NSF Ocean Observatories Initiative. So you can find data from this today, from IUS today. So basically having these gliders was one step, but all these other observing systems coming online so we can have multiple swarms of robots and moorings and HF radar coastal stations look at ocean currents. A lot of exciting things are happening. And this is where we are now. We have all these observing systems, and at Rutgers with Maracus, this is what our observatory entails for our region. We have satellite receivers at the top of the building looking at satellite sea surface temperature and ocean color. We have these CODAR 46 coastal Doppler radars looking at surface currents of the ocean, mapping surface currents of the ocean. We've had about 500 glider deployments, and all this data fed into those ocean models. And the key thing in here is that we're doing this with students, with people learning about the ocean. There's a table back here in the corner where they all do their homework. And when something exciting happens in the ocean, they can come into our laboratory, into our observatory, and they can see what's happening at sea. So we're bringing the ocean to our students, not trying to bring our students to the ocean, which can get really expensive and they all get seasick. Here they can work and care about the ocean on computers and looking at data in real time. This took a lot of collaboration and partnership. So all of these different organizations played a role in developing this. Okay, so with this observatory, what can we do? In the Mid-Atlantic, we can look at ocean features, the physics, we can look at water runoff, we can look at how our ocean interacts with coastal populations, we can look at habitats. We actually have passive acoustics that can listen for tagged fish, but also listen for whales. So we can monitor whale movements. We can look at climate change. So we can have all these data sets out there over many, many years that build up into this long climate scale data set. And then what my favorite part is working on storms and hurricanes. So this is our critical science themes that affect our local communities that we use our observatory for. Okay, now moving back to those tropical storms. How do we use gliders in ocean observing networks in hurricanes? This is a second breakpoint if anyone has a couple of questions, and then I'm going to move on to the rest of the talk until we finish.
Okay, so we had one or two questions from earlier, Travis. One was about the accessibility of Argo data to scientists in other countries, as well as to the general public. If you could comment.
Yeah, Argo data, I believe, should be publicly available to all people, as long as there's no firewall stopping you from getting to the site. It should be available to classrooms. I think there's even tutorials for how to use it for classrooms, but I think it's publicly available to everyone, as is a lot of our ocean glider data. I think most of it is publicly available. If it's on the website, it should be available.
Yeah,
I've had some. Yeah, go ahead.
Oh, I was just going to say, I believe that also if just even simply doing a Google search through NOAA and Argo, you can find some of that data.
Yeah, yep.
Yeah.
Sometimes there's challenges with bandwidth. Some of the Argo data is not too big, but the glider data can get very large. And so just depending on where you are, sometimes there's limitations, but it should be freely available to at least try.
Right, and I believe sometimes you may need an oceanographer to help you decipher the, uh,
Yeah, yeah.
the data sets that are presented because they're traditionally meant for scientists.
Yep.
One thing I'm hoping that you might be able to comment on pretty quickly is that you had mentioned maracus
Yep.
in one of your earlier slides, and I'm just wondering if you might just be able to comment on what maracus means and its relationship to IUCE and how IUCE breaks up the United States into various regions for monitoring the ocean.
Yeah, I think I read the acronym for maracus earlier, but I don't necessarily think reading the acronym is very helpful. It's the Mid-Atlantic Regional Association of Coastal Ocean Observing Systems. I wouldn't get hung up on the acronym itself, but the point is that IUCE has 11 different regions. It breaks the entire US and its territories up into 11 regions. And there's funding that goes into essentially developing and building and supporting ocean observatories in each of those regions for their regional needs. So I'm at Rutgers in New Jersey, which is maracus, which is the Mid-Atlantic region. There's Socorro, which is the South Atlantic region, and that goes from kind of Florida all the way up to North Carolina. There's Caracus, which is the Caribbean, like Puerto Rico, Virgin Islands, and a little bit connected to Florida. There's Gulf of Jicus, which is the Gulf of Mexico. There's, I think, two or three in California, one off of Oregon, and then one off of Hawaii, and maybe one more floating around. There's Alaska as well. So every region, if you're in the US, every region that you live in has a CUS or a ooze in it. And a lot of them have gliders, a lot of them have other technology that's key for that particular region, whether it's wave buoys, near a CUS, Mid-Atlantic, or near CUS, which is in the Northeast, so Gulf of Maine. So whether they have buoys or gliders or whatever it is. And those are all generally made up of academic institutions. So all the regional academic institutions get together and they work together collaboratively to provide data for the good of their region, but also the good of the nation, and do research at the same time. So for maracus, it might seem a little weird that I work on tropical cyclones, but that's actually the next part of my talk, how I got into that. But yeah, so if you search for IUCE, go to their website, iOOS.org, I think is it, and you'll find your region on there and kind of who works on what.
And you know what? One last question, then we'll get back to the presentation, which is probably what a lot of people want to know. What do these gliders cost and who pays for it?
Yep. So that's a great question. So they cost about $150,000 to purchase, and they cost about $50,000 to $60,000 to operate for a month. Now that might seem like a lot of money compared to my salary or any of our salaries or anything like that. But when you think about how much a research vessel costs, it's actually quite a bargain. So a research vessel can cost upwards of $80,000 per day to run, to go out and collect data and do the critical science that we need to do for to understand climate change and sea level rise and all of those things. So in just a few days of ship time, you could actually purchase and operate a glider for a month. Now, gliders don't replace ships. Gliders can supplement ships and they can make ships more efficient. So we can collect some of the boring data. We can just collect temperature and salinity, things that don't really need a person to be there to understand. while the ships go and do very targeted, focused research in critical areas, can do experiments on board at sea. And we take this model, we do this a lot actually in the Antarctic, where we'll take a ship. That ship's time is very, very valuable because it takes so long to get there. And we'll deploy multiple gliders, and they'll go and do survey work while the ship stays in one spot and does some really critical experiments.
Thanks. Thank you. All right, why don't we move forward?
Okay. So this is the last segment, and this is how gliders got into being hurricane sentinels, as we call them. So this is 2011. I was a graduate student at Rutgers. This is Hurricane Irene. It's coming up the coastline. I don't know if anyone who said they've been in a storm was in Hurricane Irene, but it was coming up the coastline, and we actually had a few gliders deployed. So this is RU 15. It's actually supposed to be 16. So this is RU 16 down here. And it was deployed for the state of New Jersey Department of Environmental Protection. And it was there to look at low oxygen zones in the summer. There's another glider that became disabled that was doing work for Marcus. I'm going to focus just on this glider down here. So Irene was coming up the coast. We talked to the state of New Jersey DEP and asked them what they wanted us to do with the glider that they were paying for. And they said, leave it out. Go collect as much data as you can. So Hurricane Irene, it wasn't the strongest storm, but in my scientific career, it's been the most important storm. So pre-Irene, there were many different warnings telling people to flee the storm's path. Obama saying it's going to be a historic hurricane, to be prepared. New Jersey governor, this is going to be an enormous storm. Everyone's saying it's going to be the worst in the world. For storm surge specifically, it was forecasted to be this really devastating storm. Well, it was devastating, but it wasn't a storm surge storm. It was a rainstorm. So it rapidly weakened right before making landfall, and it actually drenched inland. So this is at the Rutgers Boathouse, and Rutgers is about 30 miles inland from the coast. And the coastline storm surge, really little to nothing happened from Hurricane Irene. So as we were standing out here, we were thinking about what went wrong with the forecast. What piece of this didn't we understand, or what piece as we as oceanographers can help understand? Here's that forecast. So this is the official forecast. And what you're seeing here is wind speed. So again, that intensity, and here's time. The black line is the official after the storm analyzed best track estimate of the intensity. So this is the best estimate of what the intensity actually was. Each of these colored lines represents a forecast cycle. So you remember in the beginning when I said how a forecast is made, they did this over and over. And the models and everything pointed to the storm strengthening all the way up to a category 4. And all the way up until landfall, it was forecast to be a category 1 or a category 2. So we started to look at our observatory data to understand what was happening. Hold on one sec. I'm going to switch my audio real quick. I think. Okay, if you guys can still hear me.
Yep, you sound fine.
Okay, great. So we went to our observatory to look at what happened in Hurricane Irene. Why did it weaken so much? And the first thing we looked at was our satellite data. So this is sea surface temperature. It's warm ocean ahead of Irene. After Irene, it cooled dramatically. So this is 11 degrees Celsius. That's huge. 1 degree Celsius of cooling is enough to weaken a storm. So it had 11 degrees C. It's a huge amount. And when we looked at that cooling, and we looked at this was 2017, but we looked at some research papers and data, it looks a lot like what's known as the cold pool. This cold water that's sitting at the bottom of the mid-Atlantic. So you remember earlier when I mentioned that warm water at the surface is not all you need to know. You need to know what's happening at the bottom. So in the mid-Atlantic, we have this very warm surface water in the middle of summer in August that caps off this cold bottom water. If you've ever been to the Jersey Shore on a hot, blistering day and thought you're going to go in the water, well, you usually get a surprise from how cold the water can be on these blistering days with upwelling winds. So that cold water can actually outcrop and freeze your toes when you're trying to cool off. So what happened, so this is I lost my mouse again. On the bottom left, this is temperature data from the glider. So the y-axis is depth. The x-axis is time. So this is a cross section. The glider's sitting in about one spot collecting this data. You can see warm, so the red, warm temperatures at the surface, cold temperatures at the bottom. See if I can get my mouse back again. There it is. Okay. Okay. Warm at the surface, cold at the bottom. If we look at these surface current maps from our HF radar, which I didn't talk much about, but is pretty cool, you can actually see the eye of Hurricane Irene. You can see this onshore flow in that surface. So you have onshore flow in this surface layer. It piles up all this water at the coastline, and that water comes back out the bottom, and you actually get shear and mixing across this thermocline. And this happens ahead of eye passage. And so that's really important that it happens ahead of eye passage. If a storm goes over warm water, it'll stay strong. But if it goes over cold water, it'll rapidly weaken, like I talked about earlier. So the storm actually came through like a lawnmower and just sheared off that warm surface layer and de-intensified itself. It actually had this feedback on its own intensity right before it made landfall, and it weakened rapidly. So here's that process right here. Head of eye center, you had the shear, mixing, cooling, reduced the intensity, and it reduced the storm surge. So this is a really exciting finding. And when we did some tests with our atmospheric models, where we put a warm ocean underneath our atmospheric model and a cold ocean underneath our atmospheric model, and we looked at what the wind speeds looked like. So these are two different maps of the wind speeds from our atmospheric model sensitivities. We went from a Category 1 hurricane with the warm ocean to a tropical storm for the cold ocean. So we reduced the wind speed by 10 knots just by changing that temperature a little bit. Okay, so we did that work with our gliders and with our atmospheric models and our ocean models. We went and we published that in Nature, and we thought we were going to declare victory, that we were done, that everything was great and we had succeeded. But that was really the beginning. So this was back in 2016 when this was published. We collect the data in 2011. It takes a while to publish. But the next step, the next thing we got asked to do by our friends at IUCE, the National Weather Service, at NOAA, was to turn what we had learned into something operational. So to take, not just write this research paper, but to take that research paper and turn it back into operations. And so to do that, we went to our partners. So this is all of the different people we've started to partner with since Hurricane Irene in 2011, when we learned about how storms work in the Mid-Atlantic Bight and how gliders could help us understand how the ocean was evolving. So this is all those different regions. You can see some of those IUCE regions, Caracus, Sakura, Maracus, all of them in here. But you also see the Navy, you see international organizations. Everyone is interested in how this is going to work because of all those damages hurricanes can cause. And so this was in 2018. We had 57 institutions partnering, and we wanted to deploy a Sentinel glider fleet. So to get fleets of gliders, not just one glider out there, but fleets of gliders protecting the U.S. coastline. And there was an annex written, a memorandum of agreement between NOAA and the Navy, and we started some partnerships with them. The Navy has tons of these gliders, and they're really interested in storms in the oceans. So our new approach, you can see it here. You guys have all heard of the hurricane hunters, probably. I think they've been on Planet Stewards before. They've been doing their work since 1946. And the analog is the hurricane hunters. They go out, they chase the ball, they put observations in the water and in the atmosphere to understand what a storm is going to do at any given point. What we're adding is the goalie. So we want to protect our coastlines. So while hurricane hunters are understanding what a storm's doing as it evolves, we're trying to add in data right at the coastline to understand how a storm is going to make, how strong it's going to be when it makes landfall. So you have the yellow jersey here, the goalie, and our yellow gliders here. So with us together, we can really cover a lot of territory. This is 2018, so you guys saw those gaps I was talking about. Here's those Argo floats. Hurricane hunters can go in and drop in measurements wherever a glider is going to be. But in these gaps, in these spots, this is where we want our gliders to patrol. So the mid-Atlantic coast, the South Atlantic coast, the continental shelf off of the Gulf of Mexico, and these little areas in these blue patches, areas between the islands where Hurricane Maria came, and we want to extend this observatory down. We even had one in the middle of Tropical Cyclone Alley, so this is where hurricanes form. So we're starting to build out a complete map. This is one snapshot of where all those gliders were last year. So this is 30 different Sentinel gliders out on one single day. So each of these tails represents a glider that reported data on that particular day. And we have this one picket line of gliders, another down here in the Caribbean, and one out here in this tropical South Atlantic. And you can see 3 storms on that same day. Hurricane Florence approaching North Carolina, Isaac approaching the Caribbean, and then Helen out to sea. Throughout that whole season, last year, 2018, we had 62 community gliders deployed. It's 123,000 profiles. It's 20 times more ocean data than was ever collected in these regions in a hurricane season like that. So it's really astronomical. A lot of these are Navy gliders. You can see the Navy tails. There's NOAA gliders. These are NOAA AOML, which is an organization in Florida. And then you can see the academic fleets in their home regions, in their IUS regions. So we built out this observatory and we had all the data sent to shore in real time. So we're currently analyzing that data, but there's 2 storms we captured. But the 2 major storms we captured, we had data in. So Hurricane Michael was that Category 5 storm that came up and hit Florida. It rapidly intensified over warm ocean features, and there were 7 Navy gliders in the area that was part of our coordinated fleet sending data back. So you can see all these different triangles here. They're the gliders. There's one triangle right here who's my hero, who's right under Hurricane Michael, right as it intensified into a category. It actually has been reported to be a Category 5. So right here, it actually became a Category 5 in the most recent report. And then Hurricane Florence. There were many gliders out across this whole region. There were a few directly in the path. So this is Category 4 at maximum. It rapidly weakened ahead of landfall and had record-breaking rain. And so there's many NOAA and academic gliders throughout this fleet. So we had Navy in the Gulf and many NOAA and academic fleets out here. So this is just a taste of what we can do. We're still analyzing the data for those. You saw that it took from 2011 to 2016 to write that Nature paper. So it takes a lot more time to do the science than it does to collect the data. So we're hard at work on that. But we have planning underway for more gliders in the 2019 season. So I have one more question, and that's when does the 2019 hurricane season start? And so I think that's a type-in answer that Bruce is going to do.
Right. So if everyone can just go over to your keyboards and type into your question panes, let us know. Let us know what is the first day of hurricane season. Let's see what everyone's knowledge base is. And while folks are typing that in, just a question for you, Travis. Right now it seems, and please correct me if I'm wrong on this, but right now it seems that you are able to um, take this data and sort of be able to sort of analyze the intensity of the hurricane, the strength of the hurricane, based on the water temperatures that are in the path of it, and potentially what it will do. I guess the question is, what kind of predictive capacity are you looking for in the near term and possibly in the long term, which will help regional managers or folks in NOAA's National Weather Service with their forecasting of hurricanes to be able to provide warnings for folks?
Yeah, so I don't have a specific answer for you, but what we're trying to do is improve the ocean models that are coupled to the atmospheric models in regions where there just has not been a history of observations that have been capable. So what that means is understanding how ocean temperatures on continental shelves right before landfall contribute to um, rapid intensification or rapid weakening. There's very, very little ocean data in the middle of hurricanes. And so being able to put these out there ahead of time, they give us some understanding of whether our ocean models are either totally right or totally wrong, and maybe our physics are right or our physics are wrong. And so we're just now starting to be able to do those experiments because we have these validation data sets. So the ocean is your fuel source for these storms. And no matter how much you get the physics right in the atmosphere, if you have the wrong amount of fuel or the wrong type of fuel, you're going to get the wrong intensity forecast. So we're trying to really reduce the uncertainty in the ocean as how it connects to an intensity forecast for a storm. Part of this is research, but part of this actually happens in real time. Having these data out there, they're assimilated directly into real ocean models, operational ocean models, and they can keep those ocean models on track in real time. So we can do that today. The experiments right now are kind of like how do those ocean models do at ingesting this type of data, and what sorts of impacts do they have? So we're working on that as we speak.
Okay. So getting back to your earlier question, the date of hurricane season, we have June 1st, June 1st, June 1st, August 1st, March 1st, April 1st, May 30th, August 1st, March through April, June 1st, June 30th, June 1st, June 15th. So,
All right.
the answer is Dr. Miles. Sorry.
So June 1st is the official start date, but you can get storms earlier than that. Storms don't care what our calendar says. So the key there is be ready. I put the link in the middle down there for hurricane preparedness. Last week was Hurricane Preparedness Week. So if you go to that link, you'll see some materials there. But really, we've already in the Indian Ocean, there's already been a big storm that hit India. That's Cyclone Fani. So internationally, they're already a problem. They can come early if there's been warm ocean temperatures and the right conditions. So it can go today, and then Hurricane Sandy went all the way to Halloween. So it can go from about now all the way to Halloween is the time period to be focused on hurricanes. And so the first link I put there was to National Hurricane Center. That's where you can get all your official information. There's the preparedness link, and then the bottom link is the blog for our lab. So if you guys want to see what we're doing throughout the 2019 hurricane season, where we're putting gliders, that blog will start getting posts probably in the next month or two. So when you see a hurricane coming, first make sure you're safe, check all that information, but then if you're safe and interested, go and check out our data, and you'll see where we're putting gliders and be able to follow some of the data in real time. So I want to thank the funders, so Rutgers, IUS, NOAA Ocean and Atmospheric Research, Marcus, the U.S. Navy and Naval Oceanographic offices for a lot of their support for this work, and then all the different partners listed to the left. I'm happy to take questions. So thank you all for sticking with me into the evening, and I hope you learned something.
Thanks, Travis. I think we did. I know I certainly did. I have just a couple of questions over here, and then I have some additional resources to offer as we're getting close to time. But two questions are, one, what are some of the latest sensors that have been added to the gliders? And two, you originally stated that gliders dive to a depth of about 100 meters. That's why there were sort of gaps along the coast. Do some of the newer gliders, do they have capabilities of diving to less than the same 100 meters depth?
Oh, absolutely. So gliders can operate from 5 meters down to 1,000 meters. So we actually work in the very near shore, and we do that type of work for looking at hypoxia, looking at oxygen, looking at fisheries, water quality, things like that. And then a standard glider can also go down to about 1,000 meters depth. There are new versions of gliders made by, I believe it's the JPL, Joint Jet Propulsion Laboratory, and University of Washington that can go down to 4,000 meters, so really, really deep depths. But really the shallow areas is where the type of gliders we use they're best. Some of these sensors, some of the exciting sensors. I mentioned pH for ocean acidification. That's a really important one. It's a measurement we've been able to do for a long time, but usually you have to do the chemistry yourself on a boat or with actual samples. The sensors, they've been on buoys and moorings, but they've never been able to rove the oceans. And so now that we've gotten pH on gliders, we can actually sample regional ocean acidification. So look out. I'm actually going to suggest a speaker for Planet Steward someday when she's ready. Grace Saba, she does ocean acidification throughout the Mid-Atlantic using gliders to do this, and it's very exciting stuff. And she's head of the Mid-Atlantic Coastal Acidification Network, or she's helping coordinate it. I don't know if she's technically the head, but she's at Rutgers as well. And then other sensors, there's turbulence sensors that can look at detailed turbulence in the ocean. There is laser sensors, look at particle sizes. We can look at, there's cameras that can look at zooplankton and phytoplankton. Basically any sensor you've heard of, as long as it's small enough to go on a glider, it probably has been put on one. Trying to think of other exciting ones that we've had recently. We have an echo sounder. So, and I think NOAA Southwest Fisheries Science Center also has echo sounders that we use in the Antarctic to look at krill and fish. There's passive acoustics for listening for whales. So that's something exciting that's happening, listening for right whales in areas of offshore development. Yeah, I could go on and on.
Well, thanks. It really is a fascinating field with the range of technology that we can put into these autonomous vehicles beneath the ocean as well. And thanks so much, Dr. Miles, for coming and contributing to NOAA Planet Steward's education community this evening. And we're sort of running on the very edge of time. And what I'd like to do is just to go back, and I have a few slides left before we end this evening. I'd like to let people know to please go to their emails and that they've gotten a link to our post-webinar poll. If you could please take it right after this broadcast, we'd be very appreciative. In addition, there are many other education resources and data resources that we have. This is the link to the it's a huge series of education resources directly from the IUS Integrated Ocean Observing System website, which you have over here. And then we have a whole series of NOAA education hurricane resources that come from all around the country and all across NOAA. And here is the NOAA National Weather Service Hurricane Preparedness Resources, which you see, which Dr. Miles had in his presentation, as well as NOAA National Ocean Service Hurricane Resources with a series of videos and infographics and a lot of wonderful information. And we actually do have two archived webinars that we note here, and one was actually given by woman who is a NOAA hurricane hunter scientist down at the National Weather Service Hurricane Research Laboratory, as well as Get Serious About the Weather. It's all about teaching students about extreme weather and preparedness. Those were two webinars that we did somewhat recently. And for those of you who came in late, we just wanted to let people know that to check out The Earth Scientist, where you can find out a lot more about NOAA Planet Stewards, educators, and the research that they've done and the projects they've done in their classrooms, as well as opportunities that NOAA has for you to take part of with citizen science, with national marine sanctuaries, with marine debris projects. And just wanted to reiterate that the workshop that we have going in South Carolina in NOAA Planet Stewards in collaboration with the National Estuarine Research Reserve System, June 18th through 20th in Charleston, South Carolina, just coming up. And if you want more information on that, just go to the Planet Stewards upcoming events webpage on our website, and you'll find it. And I thought that we would take this opportunity, if any, we can ask some more questions. But and of course there's the watch. I was telling people about this, our bi-monthly newsletter for educators. Just sign up for it by going to the website. And then we just thought we'd end. We've been talking a lot about hurricanes, about terrible weather, and we know that a lot of people have been getting a lot of rain, but fortunately and hopefully people will be getting some wonderful scenic views and some flowers. We thought we'd take this opportunity, this moment of zen before we go offline. I just want to see if I just wanted to thank everybody for being here and spending time with us. And we look forward to seeing you again soon at the next NOAA Planet Stewards event. And Miles, Dr. Miles, do you think you might have a moment or two for one or two more questions?
Yeah, I'd be happy to.
Okay, well, I will stop this recording and thank everyone, and thank you for taking your time for being here, and we'll take a few more questions. So thanks very much.